All right, momentum. If you look up at the top here, my basic definition is the product of an object's mass and velocity. The equation that's written here says P equals m times v. Yes, P is the symbol for momentum. I'm assuming m has been used enough times and they got sick of it, or perhaps the p is in reference to the product of an object's mass times velocity. Either way, the units are relatively simple. Mass units are kilograms, velocity units are meters per second, therefore giving us the ever so popular kilogram meter per second. Okay. I've also heard it just called kilograms times meters per second. I prefer just to say it all at once, kilogram meter per second, but that is the appropriate unit for momentum. And you've most likely heard of this term in sports where, a team's really got a lot of momentum right now, generally referring to, them winning a lot or really doing well on the field where they're kind of rolling along and they're very hard to stop. Same thing with momentum. If you have a lot of momentum, it generally requires a very large force to try to slow you down. Okay. Now there's a Newton's second law connection to momentum, and it's actually because Newton's second law wasn't originally written as the sum of the forces is equal to mass times acceleration. It was actually written as the net force is equal to the time rate of change of momentum of an object. So originally this law was written not as this, but as this. Okay. Now, it's fairly evident where that came from, because if you look at acceleration is a change in velocity over a change in time. So really, if I look at this, okay, well, that'd be m, and a would be delta v over delta t. Well, this, delta p, being a mass times velocity, would be pretty easily replaced with an m delta v, a mass where its velocity is changing. Now that's not to rule out that, say, the mass couldn't change, the velocity could stay the same and the mass would change. That would change the momentum, but more often than not, the velocity is what is going to be changing. So this was kind of the original way, right here, that Newton's second law was written. For IB students, you're going to see this particular equation on your equation sheet. Both AP and IB will have this one. Okay. All right, now this term right here, this delta P, has another specific name, okay, and it's referred to as impulse. Okay, a change in momentum is referred to as impulse. Okay, so this delta P, which is oftentimes written as m delta v, well, if I go back up and I look at this, could I rearrange this so that delta P equals something else? Sure, if I bring my delta T up, okay, then I could also say that impulse is also a change in force, or not the change in force, the sum of the forces times time. Okay, this is all called impulse. Now, in IB, I think you're going to see I, oftentimes used for impulse. In AP, you're going to see J. And again, don't ask, I'm not exactly sure as to why that is, it's just what you're going to see. Okay, now J has been used as a unit of joules for us. Now J stands for impulse in AP. In IB, you're going to just see I. So you might also just see I instead, which is fairly easy to remember since impulse starts with I. So what exactly is impulse referring to? Well, if I look at a graph, okay, and let's say I strike an object, okay, and maybe I'll use a force plate. That's a pretty easy thing to do. If I take a force plate and I drop a ball of some sort on it, if that ball has a certain mass and I drop it from a certain height, okay, it's going to hit it with a certain velocity. It might provide a force reading that looks something like this, where it's going to provide a spike with a maximum value. Now chances are that this is going to look a little more like this, okay? But for the most part it's going to look fairly much like a triangle, okay? So there's going to be this maximum force that it supplies, okay? Now this area underneath this triangle, if we look at it, in order to calculate that area, you'd have to take the force times a time. And since it's a triangle, 1/2 force times the time. But if I look at this, okay, well, force times time, that's impulse. Okay, so the area on a graph, on a force versus displacement, or I'm sorry, force versus time graph, will give us the impulse for that particular object. Now, why does this matter? Okay, well, if you look at this equation, it says your change in momentum is equal to mass times delta V. Where this really comes in handy is when we talk about car crashes. Why do you have airbags in car crashes? Okay. Well, the mass of you and your car are eventually going to come to a rest. Okay. Now the force that acts on you is really dictated by the time it takes for you to come to a stop. Because if I look at this, your mass stays the same. The change in velocity is going to go from however fast you were traveling down to 0. So that delta V is pretty much a constant. And right here, your force, that could go up or down depending on the amount of time. And if I rewrote that as F is m delta V over delta T, if this stays the same, if this numerical value is a constant, then the faster you stop, the higher the force. The longer it takes for you to stop, the smaller the force. So, you know, I tried to think about why exactly do I have an airbag? Well, the airbag inflates, and my face hits the airbag, and then I compress the airbag a while, and it takes me a while to actually come to a stop. If the airbag wasn't there, my face would slap into my steering wheel. That would be a fairly abrupt stop because it's fairly solid. Okay, it's why your dashboard and your steering wheel is padded as opposed to hard metal. Okay, the softer the surface, the better off you're going to be in a collision. So because this impulse is technically a constant value, m delta V is a constant value, in order for me to decrease the maximum force, I have to increase the time. So provided I had the same exact area, in order to reduce that minimum or reduce that maximum force, if I increase the amount of time, you notice that the area, and I'm saying these two areas are the same, this would provide a smaller maximum force, which is good for you in a car crash. Okay. All right, last thing, and this probably will take about 10 seconds, conservation of momentum. I lied, more than 10 seconds. Conservation of momentum basically states the same thing that the conservation of energy stated. Whatever momentum we have initially must equal the momentum we have finally. Okay? Or in other words, the total momentum must remain constant. So if, and I always think of a tackle in football. If you've got a guy who is standing still, essentially, when he catches a ball and he hasn't turned around to run up the field, if a linebacker tackles him at a certain speed or at a certain velocity, then prior to the collision, one person has no momentum and the other person has all the momentum, their mass times velocity. Well, if they were to tackle one another, and let's say they have the same mass, well, when they tackle each other, you've now doubled the mass of the object. They're now 1, which means in order to conserve momentum, then their velocity would have dropped to half of what it originally was. Okay, and that would have been solely in the guy who was running after to make the tackle. Okay, so after the collision, they move slower than what the linebacker who made the tackle was originally moving. I think conservation of momentum is pretty easy to see when we talk about collisions, which will be tomorrow. So we'll talk about some more circumstances. We'll talk about elastic, inelastic, and recoil type collisions. But conservation of momentum is pretty massive in that particular concept. Okay, so two objects slapping against each other. Okay, this is where conservation of momentum really comes in. If you've got one object that's initially at rest like this, and you've got one big one coming in. Okay, one object gets sent off fairly fast, the other one slowed down a little bit. Okay, so these balls, and I apologize, the surface isn't real level, but for the most part when they collide, some of the velocity from one object gets transferred to the other. This is kind of an idea of conservation of momentum. Okay.